In the 3rd century BC, King Hiero of Syracuse handed Archimedes a gold crown and a difficult problem: prove the crown was pure gold without damage in it. Since Archimedes couldn't melt the crown down into a simple cube to calculate its density, he had to find another way to measure its volume. The solution appeared when Archimedes stepped into a tub at the public baths. He noticed that the water level rose in direct proportion to his body entering the water, spilling over the sides as he sat down. This relationship between an object's volume and the amount of water it displaces allows us to calculate the exact physical forces acting on any object submerged in a liquid. On land or in water, gravity exerts a constant downward pull on every object. When a block enters the water, its weight continues to pull it toward the bottom of the container. However, the water resists being moved. It pushes back against the bottom and sides of the block with an upward force known as buoyancy. Every interaction between an object and a liquid results in a physical contest between this downward weight and the upward buoyant force. We can measure the exact strength of this upward push using a spring balance. In the open air, this stone weighs exactly 300 grams. As we lower the stone into a beaker of water, the gauge drops to 200 grams. At the same time, the stone pushes a specific volume of water through the overflow spout and into a secondary container. The stone still has the same mass, but it now has an apparent weight loss of 100 grams. This represents the strength of the water pushing up against the stone. Now we weigh the water that the stone pushed out of the way. On the scale, this displaced water weighs exactly 100 grams. The weight of the displaced water matches the upward buoyant force perfectly. This is Archimedes' principle. Any object submerged in a fluid experiences an upward force equal to the weight of the fluid it displaces. Consider why a solid iron nail sinks instantly, while a ship made of thousands of tons of steel stays afloat. Teachers, please pause the video here to let your students discuss how displacement plays a role. The nail is small and dense. Because it moves very little water out of the way, the upward buoyant force is too weak to resist its downward weight. The ship is engineered to be hollow. Its wide hull moves an enormous amount of water out of its way before the ship can sink. As the hull displaces more water, the weight of that displaced fluid and the resulting upward force increases. The ship stops sinking the moment the weight of the water it has moved aside is equal to the total weight of the ship itself. Floating depends on whether an object's shape can displace enough fluid to generate an equal upward force. You feel this physics when reeling in a fish. While submerged, it feels light. The fish displaces lake water, creating an upward buoyant force that helps lift it. But the moment the fish breaks the surface, the line suddenly feels much heavier. Without the displaced water, the buoyant force disappears, leaving you to support the full weight of the fish against gravity. Let's review. First, gravity pulls down, while buoyancy pushes up. Second, submerged objects experience an apparent loss of weight equal to that upward push. Finally, the buoyant force exactly equals the weight of the displaced fluid. Understanding the physics of floating means understanding how to displace the right amount of water.